In question number one, we have a right cylinder that's cut parallel to the base. And the shape of the cross section would be a circle. So if you have a cylinder and you're cutting it parallel to the base, it would be a circle. And if you're cutting it perpendicular to the base, then it would be a rectangle. It can't be a cone because it's got to be a 2D slice of a 3D shape. So that's going to be a circle. For question number two, we are taking a rectangle that is 4 by 7 and we are rotating it around one of the 4-foot sides. So I just put the 4-foot side over here this time. And we're going to see it on both sides of that line when we rotate it around. And just like a piece of paper, when you fold it, it's going to look cylindrical. So we are going to have a cylinder with a radius of 7 and a height of 4. And that's answer choice number 2. In number 3, we have two shapes that we need to find the volume of in order to make the full greenhouse. We need to find the volume of the half cylinder on top, and we need to find the volume of the rectangular prism on the bottom. So some people during class were asking if you needed to subtract the empty space inside, and the answer is no, because it's a tent. Oh, sorry, it's a greenhouse that people can go inside. You can walk through it, and the whole greenhouse contains plants. A greenhouse is like a place for plants. So it's all usable space inside the greenhouse. It's not like it's not part of the greenhouse. It's part of the greenhouse, all of the space inside. It's like you can walk into it, you can walk around the greenhouse. That's all part of the space of the greenhouse. So volume of the half cylinder, let's do that first. So volume of the half cylinder. On the Regents exam, you will see the volume of a cylinder formula given as capital B times H, and that's how it will be provided to you on the test. And since it's a cylinder, 1/2 capital B times H, and we know that since the base is a circle of a cylinder, the area of a circle is pi r squared. So capital B is pi r squared times the height. So if I just substitute in now, the diameter is given as 20, so that means the radius is 10 feet. And the height is 45 feet. So if I type this into my calculator really quick, 45 times 10, and then half of that. So 225 pi is the volume of the half cylinder. And that everything was in feet, so that's in cubic feet. Always pay attention to your units. And then finally, the volume of the rectangular prism. And prisms are capital B times H. And since it's a rectangular prism, that would be length times width times height. So here, that would be 12 times 20 times 45 feet. And that would be 12 times 20 times 45. That would be 10,800. And once again, it's in cubic feet. So all I have to do now is add the two volumes together. So on my calculator, I'm just going to add 225 pi and oops, I forgot to square the 10. So it's 100 times 45. My bad. I'm trying to do this video quickly so I can get it out for you guys as soon as possible, since I did leave my iPad at work over the weekend. So I'm always making little mistakes like that. So 100 times 45 is 450. 100 times 45. So it's half of that. So 2,250 pi. So that's what I'm adding to the 10,800. Let me find that value. And that was once again 2,250 pi. And there we have it. 17,868.58. So it says to round to the nearest whole number. So approximately 17,869. To the nearest cubic foot. And that's answer choice number 1. Okay, moving to number 4. We are taking a cross section through the vertex perpendicular to the base, so that means intersecting the base. So that would be a triangle. If you were taking it parallel to the base, it would be the same as the base. It would be a square. Anytime you take a vertical cross section of a pyramid, you're going to get a triangle the same as the faces. Okay. This one over here might be a little bit hard to visualize. So you have a cone, you have a cylinder, and you are taking a cross section perpendicular to the base. So as we talked about in the other example before on cross sections, if it's perpendicular to the base, it's going to be a rectangle. If it was parallel to the base, it would be a circle. So it's not parallel to the base here. So not answer choice 1, not answer choice number 2, because that would be potentially it if we were parallel to the base. Let me pull up over here my cross sections of a cylinder. Let me find it over here, right over here. So I can show you guys why the answer is the way that it is. So I'm going to tilt this so it's perpendicular to the base. And notice how the cross-section slice spans the entire diameter of the circle. So that's why it might not be so clear why the correct answer is 4. But once again, the diameter of the original cylinder was 8. And take a look here, when we're slicing it vertically, it spans the entire diameter. So that's one that's a little bit hard to visualize. So it helps to see it with a visualization tool like the one I just showed you guys on GeoGebra. So now we're talking about the volume of a cone. So you're going to see it as 1/3 capital B times H. So that's 1/3. When we have a cone, the base is a circle. So that's pi r squared for area of a circle times the height. And we are given that the radius is 2.5 centimeters. And we're given that the height is 7.2 centimeters. Everything's in centimeters, so we are good to go so far. So I'm just going to plug it into my calculator. So 1/3. And then that is 2.5 squared. And then times 7.2. And, oh, I forgot the pi. And that's approximately 47.1 cubic inches rounded to the nearest tenth. Sorry, that was 47.1. And that's answer choice number 2. For question number 7, we are rotating around side AC. So when it spins really fast around AC, you can think of it as a flag rotating around a flagpole. We're going to see it on both sides. And the straight edges are going to become circular. So it's going to look like this kind of cone here with a height of 8 and a radius of 15. And that's going to be answer choice number 3. Oh, sorry. I picked the wrong answer choice. A radius of 15 and a height of 8. Oh, it looks like answer choice 1 and answer choice 3 are both correct. That's okay. A radius of 15 and a height of 8. My bad with that. Okay. Here, this one was tricky because if you take a look, the rectangular prism sandbox, the dimensions are given in inches, and in inches. But if you keep reading, the bags of sand have a volume of 0.5 cubic feet. So we do need to convert from inches to feet, else we won't be able to figure out how many bags of sand that we need. Also, keep in mind that the depth is the same thing as the height. I'm going to put that in parentheses. And that's because height is when something is tall above the ground and it goes up. But when something goes below the ground, then it's depth that we're talking about. It's how deep it goes, like a pool, how deep it goes, or a sandbox, how deep the sandbox is. So depth and height are kind of interchangeable. It's just about if something is below the ground or something is above the ground. So I'm going to just start off by converting from inches to feet. So I'm going to take each of the dimensions that were given, and I'm just going to convert each of them to feet by dividing by 12. That conversion is not provided to you on the Regents exam from inches to feet. So I'm going to do 43 divided by 12, 3.58 approximately. Okay, 30 divided by 12. And actually, I should have just left that as a fraction. No, that's the lowest terms. I could have just left it as a fraction, though. 30 over 12, 2.5. That one works out nicely. And then 9 over 12. I believe that one works out nicely, too. And that's 0.75. So now I can take my volume of a prism formula, capital B times H. It's a rectangular prism, so that's length times width times height. And I can substitute in 3.58, 2.5, and 0.75. And I can see what my volume is. And that's 6.7125. Oops. And that is in cubic feet. So now to find out how many bags of sand, since each bag contains 0.5 of a cubic foot, I can just divide by 0.5 to figure out how many of those 0.5 cubic feet bags it's going to take to fill up my sandbox. And that's 13.425, but if we buy 13 bags of sand, we won't have enough bags of sand to fill up the sandbox. There'll still be that 0.452 that is still not filled up with sand. So we are going to have to round up to 14. We will have too many bags of sand. You know, we'll have a little bit extra left over, but we'll have enough to fill up what we need to in the sandbox. For number 9, we have a cylindrical jar with a volume of 1,180 centimeters cubed. The height is also given in centimeters, and what we are finding is the diameter of the jar to the nearest tenth of a centimeter, so no conversions necessary here. So volume of a cylinder is capital B times H. Here, a cylinder has a circular base. Area of a circle is pi r squared, and then times the height, so that is the formula that we're going to be using. So we are actually finding the radius because that's going to help us to find the diameter. Oops, I should have plugged in the volume. Let me do that. They give us the volume of 1,180 cubic centimeters. Once again, we are finding the radius. And then the height is 10. So what I'm going to do first is I'm going to move everything away from the r squared. And I'm going to do that by dividing both sides by 10 pi. And that way, I can eliminate the 10, and I can eliminate the pi, and I'll just be left over with r squared. So in my calculator, I'm going to do that. 1,180 divided by, what was that again? 10 pi. And that's 37.5606. And then to get r by itself, I'm just going to take the square root of both sides. And r is approximately 6.1287. And we do need the diameter, so we're going to multiply the radius by 2 in order to get the diameter. And we are rounding to the nearest tenth, so that's approximately 12.3 for the diameter. Okay, moving down to the next one. So they give us that the water storage tank has to hold 100,000 gallons of water. So that's the volume that it has to hold. So they're providing us with the volume of this cylindrical water storage tank. And they're also giving us the height. And the height is in feet. So gallons and feet, those are not the same unit. And also, they do provide us with this conversion here from cubic feet to gallons. So that also is telling me that we are going to need to do a conversion. I am going to have to convert from the gallons to the feet. So I'm going to do that first off before I even get started. So there is 1 cubic foot for every 7.8 7.48 gallons of water. So basically, what we're trying to find out is how many cubic feet are going to be in 100,000 gallons of water. And then you can cross multiply and you can say 100,000 gallons is equal to 7.48x. And then you'll see that what you need to do is divide both sides by 7.48. Some of you might have already seen that the conversion is divide by 7.48, but there were some questions about setting up a proportion in class, so I wanted to show it. But if you already saw to divide by 7.48, that's all we're doing. We're just taking the 100,000 and we're dividing by 7.48. So 100,000 divided by 7.48. And that is 13,368.984 approximately. So that is the volume in cubic feet. So now I'm going to go to my volume of a cylinder formula, which is capital B times H. And since it has a circle base, that's pi r squared times height. And we now know that the volume in cubic feet is what we just found it to be. And the height was given to us as 30 feet. And now everything's in feet, so we can plug that in. So this is similar to the previous question where we're trying to isolate the r. So I'm going to start off by just dividing both sides by 30 pi. And once again, my goal is to isolate r squared. So that eliminates the 30, that eliminates the pi, and it leaves me just with r squared. So in my calculator, I'm just going to hit divided by, I should put parentheses, divided by 30 pi. And we have 141.849. And then to get r by itself, we're going to take the square root of both sides. And we have about 11.91. And since we need the diameter, we're going to just multiply by 2. And I think it says to round to the nearest whole number, so that would be approximately 24. And that is the answer choice over here, approximately 24 feet. Okay, hopefully that clears things up for this one from class today. Okay, for number 11, this is one where we do have to recognize that we need a conversion. We need to figure out if the 500 bricks are going to fit in the trailer with the weight, if it's going to be able to support the weight of 500 bricks. And we're told the dimensions of the brick in centimeters, but the density for the volume unit uses meters. So if I find the volume right now with the dimensions they give me, that's going to be in cubic centimeters, but my volume unit is in cubic meters, so I need to actually make sure my volume is in meters cubed. So the conversion from centimeters to meters is to divide by 100. So I'm going to do that. So instead of 5.1 centimeters, I'm going to move the decimal places 2 spots, 0.051 meters. And I have 0.102 meters instead of 10.2, and I have 0.203 meters instead of 20.3. And for a rectangular prism, which is what the brick is, it's capital B times H, and since it's a rectangular prism, that's length times width times height. So I'm going to multiply our dimensions together, 0.051, 0.102, and 0.203, and I'm going to see what I get. 0.051, 0.102, and the last one is 0.203. and it looks weird, but it's not wrong. 0.001056. And I'll just put dot dot dot. I have it in my calculator. So density is mass over volume. The density formula is not provided to you on the test or on the Regents exam. So the density is given as 1,920 kilograms per meters cubed. And sorry, this is meters cubed. And we're finding the mass, the weight of each brick. And we just found the volume in meters cubed. So what we can do is we can put this over 1. We can cross multiply. And the great news is that the meters is going to cancel out. And our mass is going to be in kilograms, which is what it should be, because the maximum capacity of the contractor's trailer is 900 kilograms. So we want our weight to be in kilograms. So I'm going to multiply by 1,920. And I got 2.027. And once again, I have it in my calculator. So that's the weight of one brick. So to find the weight of 500 bricks, I just need to multiply it by 500. And that's 1,013.8 approximately. So that is over 900. So the answer to this question is no. The trailer can't hold the weight of 500 bricks because it exceeds 900 kilograms. It's over 1,000 kilograms. The next question is about Cavalieri's principle. So you can check out the answer key for a really nice written up response. In this video, I'm just going to talk about the components that should go into it, but I wrote the response up already in the answer key, so please check that out. So for Cavalieri's principle, it's 2 parts. The first part is same heights. And the second part is the cross section area. So the area of the cross section should be the same. And if these two things happen, then the figures have the same volumes, whether one's right and one's oblique, which means if one's standing up straight and one's slanted, it doesn't matter. Even if they're two different 3D solids, it doesn't matter. If these two things are true, they're going to have the same volumes. So you can't just write what Cavalieri's principle is and get full credit for this response. You have to also use the context of the question in your response. So for example, how do I know in this situation that there is the same heights? Well, it's because in the question they tell me that both stacks have 23 quarters. So in my response, I would say, since both stacks have 23 quarters, they have the same heights. And then for the cross-section areas, I'm going to also try to use some information from the question. If I take a cross-section of either stack parallel to the base, it's going to be one of those quarters. And since each of the quarters are the same, they're going to have the same radius. So the area of the cross-section, the pi r squared, is going to be the same because each of the quarters has the same radius. Therefore, equal volumes. Once again, to see all of that written up, please see the answer key. But that is what needs to be in your response. These 2 parts are the components of Cavalieri's principle, and you also just need to bring in some information from the situation, so it's actually applying the principle to this question, and it's not just stating what Cavalieri's principle is. Finally, the last question. And for this last question over here, the wording was real confusing, but this was a real Regents question, a long response one. So both of the boxes contain the same amount of chocolate covered almonds. So that means they have the same volumes. So in question number 1, you're given that the height of the new container is 16. And you need to find one of the side lengths of the base. It does say that it has a square base, even though it says it's a rectangular prism, it has a square base. So if it has a square base, if this is one side and this is the other side, they're both going to be the same, right? Because it's a square. And if you want to find the area of that square base, the capital B, you could do length times width, S times S. So the capital B, the area of the base, would be side squared. And that's going to be important. We're going to need that for what we're doing. Also, since there is the same volumes on both of the containers, if I find the volume of the cylinder one, then I know what the volume of the rectangular prism one has to be. So I'm going to start off by finding the volume of the cylinder, which is capital B times H. And since it's a circle base, that would be pi r squared times height. And the radius is 7 because the diameter is 14. And the height is 18. So in my calculator, I'm going to do 7 squared is 49. 49 times 18. And that's 882 pi. Okay, everything was in cubic centimeters. So now, when I'm plugging in for the rectangular prism, which is capital B times H, and since it's it's a rectangular prism with a square base, so as we just spoke about, the area of the base would be side times side, because both of the sides are the same. And we now know that the volume should be 882 pi because it's the same as the cylinder. So we have 882 pi cubic centimeters is equal to capital B, which is S squared, whatever the side is, times itself, side times side, length times width, times the height, which is 16. So now all I have to do is divide both sides by 16. And that's 173.18. Wait, was it 183? No, 173. I'm just going to write ... equals to S squared because I still have it on my calculator. And then I'm going to do the square root of both sides to get S by itself. And to the nearest tenth, that's about 13.2. And it does say to round to the nearest tenth. So each side length of the base is 13.2. I also want you to remember when we go into question number 2 that on Regents questions that have multiple parts, generally your answer to the first part is going to be used in some way in the second part. So that 13.2 is going to be used in some way in the second part. In the second part, what they tell you is that you have a rectangular shelf and the dimensions are 80 by 60 centimeters. And you're trying to stack as many of these rectangular prism boxes. I shouldn't say stack. You're trying to put as many on the shelf as possible in a single layer. So you're not concerned with the height here because you're only putting one layer. You're not like stacking them, so it doesn't matter. You're only putting one layer. Now, width-wise, the width of the box is going to determine how many you can put. And lengthwise, the length of the box of the base is going to determine how many you can put. Because you can only put as many 13.2s as will fit in either direction because the length and the width, the sides of the base are 13.2. So you can only put as many 13.2s as the 80 centimeters and the 60 centimeter dimensions of the shelf will allow you to put. That's all you can put. So what I'm going to do is I'm actually going to just take both of the dimensions, the 60 centimeters and the 80 centimeters, and I'm just going to find out how many 13.2s can go in each direction. How many of the sides can go in each of the side lanes can go in either of the directions. Okay, so here I got 4.5, but I'm going to round it down to 4 because I can't fit 0.54 of a container on a shelf. That doesn't make sense. We don't have 0.54 of a container. But if I round up to 5, it's not going to fit. So I have to round down to 4 because 4 is the most that can actually fit in that direction on the shelf. And then the same thing here, 80 divided by 13.2. I'm going to round that down to 6 because 7 won't fit on the shelf. And then I can do length times width to find out how many containers can fit. And that is 24 containers.